This is question 11 from the second CSAT sample paper. So we're told about two methods for removing the smallest k elements out of a list of n elements, which aren't necessarily sorted. And the first method is to sort all n elements in ascending order, and we're told the time this takes is n squared units, so let's say n squared seconds. And then we remove the first k of the sorted list. That works because once we sort them, they're in order, so the first k are the smallest k, and then we just remove those. And then the second method is to scan the list. We'll have to figure out what that means, to find and remove the smallest element one at a time until we've done this k times. And we're told that the time to compare two elements is 1 unit, and the time to remove one element is 1 unit. So let's say 1 second. And what we're asked to do is to prove that the second strategy is the faster one. So if you want to have a go at this question yourself, pause the video now. Okay, so what's it going to look like to prove that this is faster? First, we're going to have to describe a way to scan the list to find the smallest element. And we don't want to use any sort of function or computing ability that we're not given. So basically we can compare two elements at a time. We can't, for instance, by some method compare all the elements of the list at once. We have to compare them in pairs. But otherwise we're free to describe the way in which we scan the list. And we want to show it's faster, so that means it has to be faster in all cases. So I think the best way to approach this is to think about the worst possible case, the worst case scenario, write down how fast it is in that case, and then compare to the speed of this case, case 1. And then we're hoping that even in the worst case, method 2 will be faster, the time taken will be smaller. And that means it will be faster in all situations. So first of all, let's try and flesh out method 2, so scanning the list and then removing the smallest element each time. We're dealing with the worst case scenario, so let's think about what the list looks like. I'm imagining that we scan it from left to right. So the leftmost element is the first element. And suppose we've got these n elements, or suppose the elements are just the numbers 1 to n, because there's n elements. Then the worst case scenario is that the k elements we want to remove are at the end. And the smallest element is right at the end, and then the next smallest, and then the next smallest, etc. Because that means if we start scanning from this end, we've got no reason not to. If we started scanning from this end, then the worst case scenario would be the other way around. But suppose we start from the left. Then it's going to take us a while to find, it's going to take us as long as possible to find the smallest element before we can remove it. And then after that, if we have to start from the beginning again, because there's no indication that we're dealing with, say, a computer with memory that can remember which is the next smallest element, it looks like we have to scan it all over again, and then the next smallest element is going to be at the end of that list, and so on. So this is always going to be the worst case scenario. So what does scanning look like? I'm saying we're starting from this end and comparing pairs to get up to here. What does the method look like? Well, what do we have to do first? We're starting at the left, so we'll take the first two elements and compare them. It's kind of implicit in the question. We do have to kind of figure out exactly what's allowed and what isn't, but it's kind of implicit in the question. You can look at any two values and compare their sizes. That's something our computer can do. So we can look at the first two elements and compare them. So comparing the first and second elements. And then we're scanning the list for the smallest element. So what do we want to do having compared the first and the second? Well, we can ignore the bigger one of those two. That's definitely not going to be the smallest element in the list. And the smaller element, for all we know at the start, might be the smallest element in the list. But we don't know because we haven't compared it to the others. So we'll have to compare it to all the other elements in the list. So now let's take the smaller one and we'll compare it to the next element, the third one along. So we compare the smaller one of these with the third element. And then whichever is smaller out of these two we want to do the same with, because then at each step we're keeping the smallest one we've found so far, and when we get to the end, the smallest one we've found so far will be the smallest element in the list. So this does mean we have to scan the whole list. So perhaps there's a cleverer way of doing it, or if we had a more capable computer, perhaps it could do a better method of comparison. But it makes sense to deal with the worst case, so we'll use this and hope that the time it takes still comes out as less than the first method described in the question. So now we're comparing with the fourth element, etc., all the way along, and then we compare the smaller element from the previous step each time with the next element until we compare with the nth element, and then we remove the smaller of the two elements at this step. So if it's the nth element, that's because it's the smallest. If it's this element, that's because it's been the smallest in every previous comparison. So we remove the smallest out of these two, and that's going to be the smallest element in the list being removed. I've written it out in bullet points like this because each of these steps takes 1 unit of time, 1 second. Because it said in the question we can compare two things and remove one thing, and that takes 1 second. So now we just got to figure out how long this takes us. So the first time we scan the list, it's going to take us n-1 comparisons to get to the end. There's n elements, that means there's n-1 steps here. And then we have to add 1 second to remove an element. So we can in fact ignore removal because both methods are going to remove k things, so they're both going to perform k removals. We might as well write down what the time actually is. So we'll include the time to remove. How long does it take us the second time we do this? So we remove an element and then we start from the beginning again. Well, then there's going to be one fewer elements, so it will just take n-2 comparisons, and then after that it will take n-3, etc. So it's the kth time we do it, it takes n-k seconds. And each time plus 1 second to remove the smallest. So now let's try and add these all up and see what the answer comes to and compare it to the answer for the first method. Okay, so I've just written out the sum I'm doing. We've got n-1 comparisons, then 1 removal, then n-2 comparisons, then 1 removal, etc. All the way down to n-k comparisons plus 1 removal. So we've got to add up all these numbers. So we can see in each of these cases we've got an n, so that's k times n, and then we're taking away 1 and 2, etc. all the way up to k, and then we're adding k lots of 1. And this thing here is just going to be a half k, k plus 1. So we get k times n minus a half k, k plus 1 plus k. So we could try to simplify this, but it doesn't really matter. What matters is us comparing it to, this is the time for the second procedure, we want to compare to the time for the first procedure. But that, we were told it takes n squared seconds to order everything, and then it does k removals, so that's an extra k seconds. So that's the time for the first method, with k removals at the end. And we want to show that this is bigger than this. So the usual way of showing, or one of the typical ways of showing that one thing is bigger than another, is to do this minus this, and then show the answers positive. And that's promising because these k's are going to cancel, obviously, because each of them involves removing k things. And then we can look at the rest of the expression, which is going to be quadratic in n, and see if it's positive. So if we do this subtraction, this time minus this time, the k's cancel at the end, we get n squared minus k times n plus a half k, k plus 1. And I want to show this is positive, but there's a minus here, which might be worrying. So actually it's kind of obvious this is going to be positive because k is always going to be less than or equal to n, so this is going to be at least 0, and then this will be positive. But let's just, since it's a quadratic, we can complete the square to get this, and then just take this away at the end, and then we've got half k squared here and k squared over 4 there. So we get this squared bracket plus k squared over 4 plus k over 2, and these terms are positive. And therefore we're getting a positive answer. So that means that the time for the first procedure is always strictly greater than the time for the second procedure. So, or to write it the other way around, the time for the second procedure is always strictly less than the time for the first.